Good morning, everybody. Thank you, Isabelle. First of all, a very warm welcome to you all here in Toulouse. I would like to open the conference with a very short and simple statement. Thank you. Thank you all for coming to the second edition of Fira. Some of you have traveled a long way, and we are very happy to have you all with us. Also, a special thank you to Fira partners. This year, over 40 institutions, companies, journalists, and ambassadors have helped us make the forum possible, and we really can't thank them enough. Before I leave the stage to make room for our speakers, I would also like to express our special gratitude to Toulouse Métropole for welcoming us here in the scientific heart of Toulouse at the Quai des Savoirs. The location wasn't chosen by accident. I mean, today, we are going to talk about agricultural robots, which means robotics, which means science. We are here together in this amazing and prestigious place to enable science, and especially robotics, answering some of the biggest challenges agriculture is facing today. Together, we want to move forward and lay the groundwork for the sector of agricultural robotics. Together, we are going to build this sector and share our ideas, thoughts, and feedback during this new edition of the International Forum of Agricultural Robotics. Today, I think I can say something. I can say that this event, this Fira, is a huge success. There are nearly 500 people gathered here, more than double the participants we had last year. However, the two coming days will only be truly successful if we get the dynamics of the agricultural sector going. We aim to make agricultural robotics more democratic and create a close-knit sector where every stakeholder participates in the new and upcoming agricultural revolution. Thank you. It's time for me to leave you. I really hope you will all enjoy the Fira. And let's turn this event into an international crossroad of science, robotics, and agriculture. Have a nice day. Bye.
Thank you very much, Emeric. Now we are beginning with the first part called Why Robots Come to the Farm. It will be animated by Isabel Baez-Betancourt, who works for several Spanish ag magazines. Please come to the scene. And with you, Simon Blackmore, Philippe Janot, Maët Leland, and Luc Valentin. Please welcome them very warmly.
Well, bonjour. Désolé, je ne parle pas français, so I will continue in English, if you don't mind. Thank you very much for coming here. I will be conducting this debate. I'm overwhelmed with this amazing audience. It's a lot of people. I didn't imagine it was going to be like this, so I will try to do my best. We have a really difficult task today, which is to answer this question, why robots are entering our fields. It's quite a question. So to help us to find the answer, or perhaps it will be more than one answer, I guess, we have our speakers today here with us. Let me introduce them. It's Professor Simon Blackmore from Harper Adams University. Philippe Janot from Vet Sub. We also have Luc Valentin, farm consultant in the USA, and Maët Leland, that coordinates the Bretagne Sud Experimental Research Station. Okay, so with no further ado, I would like to ask Mr. Professor Blackmore to begin with his presentation, please. Thank you.
Okay, well, thank you very much, Isabel. And bonjour, good morning everybody. It's a great pleasure to be here. I think this is the first time I've had the opportunity to talk to so many people in agricultural robots. This is a wonderful turnout that we're getting here, so I congratulate the organizers for doing this. So I'd like to tell you a little bit about the work that I've been doing over quite a number of years now to develop a complete system of agricultural robots. It still is very much at the cutting edge. Things are moving very quickly. But I'd like to go through some of the ideas and designs and opportunities that we've got to help to make agriculture more efficient than it is at the moment. So I come from a small university in England called Harper University. It specializes in agriculture. We set up the National Centre for Precision Farming, and we do a whole range of different research projects, including drones, autonomous tractors, laser weeding, robotic seeding and spraying, phenotyping, autonomous mowers, strawberry harvesting, and the hands-free Hectare. We haven't got time to go through all of these, so I'll just show a selection of them for you. The UK government has changed tack recently over the last maybe 15 years. Very little research money has gone into agriculture, but we've now got 4 new centres in the agricultural sector, and one of them is the Precision Innovation Centre, which is a private company at my university. And there are hubs in Scotland and at Cranfield University. But we have 27 instrumented farms now and 130 commercial collaborating companies. So the topic of today then really is to try and come up with a vision of what agriculture is going to be like in the future. And as we look forwards, we can also then look into the past and look at our current agricultural system. And although every farmer will know that they are doing the best that they can, they are good farmers, I can see many weaknesses in our current system. And one of the main areas is that the current agricultural practices use too much energy in all its different forms. And there are new drivers for change in the agricultural sector. We need to come up with more sustainable food production. Farmers need to be able to make more money, to be able to make a living wage, and we have to then look after the environment. So I believe that we need to develop a more flexible agricultural production system. Many farms and fields can be of this sort of size, the sort of prairie-type farming, but I believe that the current mechanization system is more like an industrial production line, where we are only interested in maximizing the yield. But many industries have moved over into flexible manufacturing, where we have a much more dynamic set of tools that allow the managers to be able to do things in different ways. It becomes more information intensive, but we can then be able to maximize gross margins, manage risk, and minimize environmental impact if we then use automation. Again, if we look at how machines have developed over the past maybe 50, 60 years, we can see that it has been linear development. It's been getting bigger all the time. There's a very good reason for that, and that is through economies of scale, because one of the major costs is the person sitting on the tractor. And if we can then increase the production of that person, then the investment then makes sense. But machines have now reached their maximum size. Here we've got a picture of a modern tractor and a combine harvester here. and this is being loaded onto railway wagons. And this then has to fit through a railway gauge. Now, the machines are designed to fit through this railway tunnels now, so they cannot be made any bigger. They've now reached the maximum size. But on the other hand, that gives us the opportunity to be able then to look for other forms of efficiency. So big tractors and big implements give us increased work rates and economies of scale. I believe that they've now reached their maximum size. These big machines are good for big fields and big farms, but I believe that small to medium-sized farms and fields have the greatest potential for increased production. We're all interested in agriculture. We all want to be able to feed the planet. Where is that extra production going to come from? What we've seen with precision farming over the last 20, 30 years is that very rarely does precision farming increase yield. We can reduce the cost of production. So where is this extra yield going to come from? And I believe that it's not necessarily going to come from the big farms and the big fields. I think it's going to come from the smaller farms and smaller fields that have not been able to take advantage of economies of scale of the big tractors. So the small fields and small farms are not as efficient as they could be. But with the advent of robotics, I think that these small farms and small fields can produce significantly more and become much more viable enterprises. Now, I'm an agricultural engineer and I like big tractors. Give me a day off, I'll go and do some recreational tillage in the fields, black smoke coming out the exhaust pipe, I will be very happy. But I asked this question to the farmers, obviously the tractor is stuck here, but why is the tractor stuck? Some farmers will say you have a crazy driver because you shouldn't have gone there in the first place. Some farmers will say it's the weather, meaning that the soil is soft because it is raining. I say neither of those things. I say the problem is with the big machine. You cannot change the soil. You cannot change the weather. We can change the tractor. So at the moment, one size fits all. Boys' toys, big boys' toys. I'm sure some of you were maybe at Agritechnica last week, and you will see the big machines there. But I believe that small, smart machines are just as much fun and are just as much interest to us. We cannot change the soil or the weather, but we can change the tractor. And so, of course, that's why we are here today. We are here to discuss this new form of mechanization. The big machines, although they solve lots of problems, they also cause lots of problems. Here we can see sugar beet growing, and here we can see a compaction layer in the soil that is then due to the big machines in the first place. I now estimate that 90% of the energy going into cultivation is there to repair the damage caused by the large machines in the first place. So why do we do it? Repeated damage year after year. Every year we damage, every year we repair, then we damage, then we repair. This is crazy. The economic cost of compaction in the UK alone is £0.4 billion per annum. Huge amount of money. And it doesn't need to be there. That is waste. That is due to the inefficient system. If we don't damage the soil in the first place, we don't need to repair it. And in fact, if you look at where we find the best soil structure, it is by the hedgerows, by the field boundaries, in the forests, because the natural flora and fauna create a good soil structure for us naturally. So if we allow these natural processes to occur, then we will get the right environment that we need. So we need to move towards controlled traffic farming for the big machines and ultralight machines for the robots. So I believe that there are 4 phases to this agricultural production system. We have seeding and cultivation, which I now call establishment. We have then scouting, where we've got machines that can go in and take measurements. We then have crop care, where we can do things to the plants and the soil and the field. And then we have what I call then selective harvesting. And I'll go through some examples of these. So a robotic seeding system needs to be ultralight, 0 draft force. There's some very radical ideas coming in here. I haven't got a chance to go through explaining all of these. But if we are going to change the system, then let us make sure that we take advantage of the technologies that we've got to be able to give the farmers what they need, but in the most efficient way. I challenged my students a couple of years ago to come up with an ultralight machine. So they bought a ride-on lawnmower and then robotized it. And we took it out in February, a few years back, where the soil is very wet at what we call field capacity. And where I stood out in the field to have a look at the tractor, my foot sank into the soil. It was so soft. But the following day, water had gone on top of the soil. But where the tractor had gone, across here, there was no compaction. So that's allowing these robots to go out into the field when a normal tractor would not be able to go into the field at all, which then is allowing farmers to do things that they can't do now. So crop scouting, where we can use unmanned ground vehicles. We can also use aerial vehicles, a lot of drones. People are looking at different aspects of drones. We've set up the Agricultural Drone Center, where we're developing what we call second-generation drones. So first-generation drones are flown with joysticks and with cameras and LiDAR. The second-generation drones then actually go and do things like spraying and seeding and sampling and so on. So we're developing some of these systems with different companies, but we do need to change legislation. What we are doing in the agricultural robot area is to utilize technology that's not been utilized in agriculture before. But a lot of agriculture is tied up in terms of legislation. It's stopping us. In the UK, we're not allowed to use spray drones. So we have to lobby the governments, all of our governments, to be able to allow us to use these technologies. Some of you may be aware that glyphosate has been got a renewed license for 5 years. Let me make a very important point to you. There is nothing wrong with glyphosate. We should ban the dumb machines that are applying glyphosate in the wrong places. Think about that. The problem is not with the chemical. The problem is with the way in which the chemical has been applied. So we need our work to come up with smart sprayers. I will show examples of this in just a moment. So here we have a scouting robot for vineyards with thermal cameras for irrigation status, multispectral cameras for nutrient status, and LiDAR for canopy. Here we have a sub-canopy robot working with some of the space sector people. Here we can see 1 and 2 hyperspectral cameras, omnidirectional cameras, and 3D cameras, being an instrument platform to go underneath the crop to be able to take measurements. We've then got an aspect of crop care, robotic weeding, so we're working with one of the major vegetable growers in the UK with lettuces, and here we've then got the weeds. Hand weeding, maybe some of us like to eat organic foods where we don't have any chemicals used on them. This costs £2,000 per hectare to pay people to do this work. 80% of the grass weeds in the UK are now herbicide resistant. We have a big problem with blackgrass. Don't ban glyphosate, ban the dumb machines. The chemical companies are not investing in new active ingredients. They're not developing new active ingredients. It costs so much money, $250 million in 10 years. But let's think laterally. If we have the ability to apply chemical only onto the leaf of the weed, there are many active ingredients that are available to us that we can now use. So we are working with the chemical companies to develop new machines because we have to have a symbiotic relationship between the chemicals and the machines that apply the chemicals. But there are other methods of being able to control weeds. So mechanical weeding, microdroplet, and laser weeding from 3D imaging.
Okay. Weed killer, take 2. We have to demonstrate our weed killer. It's an intelligent microsprayer which can detect the placement of weeds and apply herbicides directly onto the weeds. It consists of this tunnel inside which the plant should be moved. On top of the tunnel we have a camera, and behind that camera we have a microspray, the black box here, which have 7 distinct nozzles which can apply herbicides individually. And now let's see how it works. We place the plant in this holder and then start the robot. And now it's moved into the tunnel, and on this screen we can see what the camera sees. Now you can hear that herbicides have been applied. And on the plant we can see that the blue stuff, which is the colored herbicide, we have applied.
Okay, so we can see with some straightforward technology that most of it is, which is commercially available now, can be able then to save 99.99% of the chemical. And that is just through this new concept that I'm developing called intelligently targeted inputs. It's what you and I would do in our garden. If you've got a weed in your garden, you don't go and spray your whole garden. If you've got a weed, you go and pull that one weed out, or you put chemical onto that one weed. It's not rocket science, it's what you and I would normally do, and that's the approach that we're taking with these robots. So here again is machine vision, augmented video of weed recognition. And from this then we can identify not only the weeds, but also the little growing points, the meristems of the weeds. And if we then got that, we can apply a laser beam onto the weed to be able then to kill the weed. So the project Hyper Weeding in the UK has just finished. So we've got our lettuces, we can then identify where the weeds are, and we can then use lasers to be able to kill the weeds. So only need a very small amount of energy, and we can also spray as well. So this one is then identifying where the weeds are and then just putting chemicals onto the spray. Here we can see the machine working in real time. The flash is then the multispectral wavelengths light that we're then using, and we can see where the lasers are going, and we can see some of the results from the tests of using these two different systems. So here's one of our autonomous tractors, being able to change its navigation from RTK to LiDAR, so it identifies the posts and can steer through. We've developed this tractor that I believe now has got all of the requirements for legislation and health and safety. So we have 7 levels of safety on this tractor, and I think that that can work in a commercial environment now with the current legislation without having to change anything. Which finally brings us on to the concept of selective harvesting. So between 20 and 60% of harvested crop is thrown away at the point of harvest, which is terrible waste. Why is that? I'm afraid, ladies and gentlemen, you are the problem. I am the problem. When we go to the supermarket, if you see some lettuces or tomatoes, you pick the best one. You don't pick the worst one. This is human nature. The supermarkets pass this back to the farmers. So they will not buy anything from the farmer if it's too big or too small. And so therefore the farmers have to grade the products, and a lot of it is then wasted because it's too large or too small. But the concept of selective harvesting is again the same as you do in your garden. When you have your tomatoes growing, you go and pick the one tomato that you want. So if we put the same behavior into the robot, then we can not only pick the products that we want, but we can also grade at the point of harvest. We can add value to the products before they leave the farm. So we can have pre-harvest quality and quality assessment to do the grading and packing at the point of harvest, and be able then to, on the work that we did with strawberries, I'll show you in a moment, where each strawberry can be graded for its sweetness, its ripeness, its shelf life, and be packed at the point of harvest. So here we have one of the concept machines, and the front part is the harvester. The back part is what I now call the automated logistics. When this one is full, it can run back to the farm, and another one can come and plug itself in, but underneath here, it's then got the water, the fuel, the batteries, whatever is needed to keep the front part working. So here we've got a little bit about the robotic strawberry harvester, where we use stereo vision to grade the strawberries and to work out where the stalk, the peduncle, is. We can then go through the crop to work out where the ripe strawberries are, and the robot can then go in and be able to pick them. And as we've got control of each strawberry, rather than just dropping it, we can then put the near infrared onto it to be able to work out this one is a sweet one, this is not a sweet one, this is a ripe one, this one goes to this supermarket, this one goes to another supermarket. So we can put value into these products rather than being mass produced. They can become high quality products straight away. So there's been a lot of interest around the world for a project that we're running at the moment called the Hands-Free Hectare. This is where we are growing 1 hectare of crop without anybody ever going into the field. The crop was surveyed by drones, sampled, soil sampling with the robots. The normal operations were done by tractors and combines that we had robotized, and we did get 3.5 tons of barley that we're now going to turn into robot beer, which should be interesting.
We have modified our tractor with the autopilot from a drone, so they are conventionally used to plot waypoints around where you want to take your aerial photography from. We've adapted that system to control our tractor. We've interfaced the human controls with actuators in the steering wheel with an electric motor to convert the signals the autopilot produces to control the tractor.
Okay, so in conclusion, I think that as the title of the conference is that agricultural robots are here, I think that is exactly right. We are now at a new phase of agricultural robots. They are moving from academia into the commercial sector. I'm aware at the moment of 12 agricultural robot startup companies. And I think that now is the time where we need to think about these things in different ways and be able to let the farmers take advantage of all the opportunities that we've been able to create. I'm currently working with 2 startup companies looking for capital to be able to develop them. I think that they are going to be very disruptive. They're going to be disruptive to the farmers, because you need to think about farming in a different way. It's going to be disruptive to the machinery manufacturers and obviously to the investors as well. But it's worth it because of the benefits from it. The increased yield will then come through improving smaller fields, and collectively now we're designing these new systems and trying to understand the implications of it. Each new technology that comes along then gives us a chance to think about what the implications of that is going to be. And I'm always interested in partnerships, so very pleased to have the chance to talk to you today and be very pleased to have discussions with any of you after that. So with that, I say thank you very much for your attention.